In this video, we will demonstrate a reference design that replaces conventional DC motors with brushless DC motors in power tool applications. This design offers significant advantages such as improved lifespan, greater efficiency, and lower acoustic noise. However, these brushless DC motors require an electronically assisted commutator or driver to make them spin. This reference design was specially developed to address the challenges of implementing motor control for low-voltage, battery-powered tools. Target applications for our Power Tool Bldc motor driver reference design include drill machines, impact drivers, angle grinders, and similar cost-sensitive power tools. They require an efficient and cost-effective motor control solution that can manage high motor phase currents and maximize battery life. Measuring just 80 by 50 millimeters and with most components placed on the top side of the board, this design's small form factor saves space and power. It's also highly efficient to support field-oriented control or FOC and zero-speed maximum torque algorithms. It offers 4 shunts for motor phase current measurements and an optimized bill of materials for cost savings. Here is the functional block diagram of this reference design. The MCP1722 dual output low dropout regulator, also called an LDO, delivers 3.3 volts for the digital signal controller and 12 volts for the MOSFET drivers. The 5-volt voltage rail for the motor's Hall sensors is provided by the MCP1754S LDO. 3 MIC4605 half-bridge MOSFET drivers drive the inverter's power switches. The DS-PIC33CK64MP105 digital signal controller, or DSC, is the brain of the application and includes 3 high-performance operational amplifiers. 6 low RDS-on MOSFETs are used to implement the 3-phase inverter. There are 4 shunt resistors, each with its own current sense amplifier, to support single, dual, or 3-shunt current reconstruction techniques. The MCP9700 temperature sensor, which is located close to the inverter, monitors the temperature of the power MOSFETs. The design also includes 4 shunts for motor phase current measurement. The DSC's internal high-speed operational amplifiers condition the signal from the external shunt resistors, eliminating the need for external current sense measurement devices. The board also provides support for Hall sensors and back EMF measurement. This is a view of the top of the board where most of the components are located. Here is the bias voltage generator that is implemented using the MCP1722 dual output LDO and MCP1754S LDO. The DSC is located here and is surrounded by the current sense amplifier circuitry. The MIC4605 MOSFET drivers are located here at the center of the board. This is the 3-phase inverter implemented using 6 power MOSFETs. These are the tab-high current output connectors. The XT30 input connector is located here, and the I/O connectors are placed here on the edges of the board. The shunt resistors are placed on the bottom side of the board. Here is a summary of the technical details. The input voltage range is 12.5 to 28 volts, covering applications powered by battery strings up to 6S. The driver delivers up to 15 amps RMS for long-term operation and up to 60 amps RMS for shorter periods of time. The maximum output power is 800 watts. The pulse width modulation or PWM frequency range is 8 to 50 kHz, covering a broad range of motors' phase inductance. The maximum PWM duty cycle can reach 99%, and the driver is protected against phase overcurrent, input under and over voltage, over temperature of the power inverter, and Hall sensor interphase errors. This graph shows the motor phase current under heavy load and high speed. The driver provides a high-quality waveform for the motor phase current, ensuring low operating acoustic noise and high efficiency. This view displays the motor phase current under heavy load, very low speed, and rapid deceleration. Notice the current glitches produced by the angle interpolator. The speed of the motor decreases significantly between two Hall sensor transitions. This graph shows the motor phase current under constant heavy load and very low speeds. Again, note the current glitches produced by the angle interpolator. In this case, the glitches are significantly lower and are produced only by the error between the position of the Hall sensors and the position of the rotor. This is a view of the phase current under constant heavy load, medium speed, and advanced FOC control. Here, the rotor angle provided by the Hall sensor interpolator is continuously corrected using the information provided by an angle observer, and the phase current is glitchless. This view displays the battery current under heavy load. The current ripple is low, and the absorbed power exceeds 800 watts. Now let's take a look at a few short demonstrations for driving and drilling using our solution. In these demonstrations, the brushless DC driver of a commercial drill machine is replaced with our power tool Bldc motor driver reference design. And here we see the setup. This high-performance and cost-effective solution delivers high efficiency, small form factor, and high currents for modern low-voltage power tool applications. To learn more about this reference design, please visit the link on your screen. Thanks for watching.